All right. Our last talk of the day, Ryan Norris. I've been waiting for a CHARA speaker for quite some time. It's the crown jewel of telescopes in astronomy in a lot of ways. So I'm glad we finally got somebody to talk about it. So, Proto Dr. Norris, I will let the floor be yours. Great. Thanks for having me. So today I'm going to talk about how we can use the CHARA array to look at stars. So 2 years ago, I was on the top of a mountain in West Virginia, one of the darkest places in the eastern side of the U.S. I didn't take this picture, but this is what it looks like up there on Spruce Mountain. So if you're someplace that's really dark like this, where you're far away from city lights or really any people at all, you'll see a tremendous amount of stars. Lots and lots of stars. If you have binoculars like I have, you can zoom in and look at the stars, and you'll see more stars. But when you look at the stars, all you see are points. You see points of light. Even with the telescope, like the Hubble Space Telescope, when Hubble looks at a place where there's lots of stars, a star field like this, again, the stars are just points. And some of them have spikes, so that's from the optics. Side note, for people who like astronomy but don't do astronomy, I was at an astronomy conference once, and there was an art history student, a college student studying art history, who was presenting a poster at this big astronomy meeting about art, and about how she went through the history of art and looked at whether or not there were the spikes and stars, and she tied it to the widespread use of telescopes. So that before people were looking at stars and telescopes, they had stars as points. And then when they started looking at telescopes, they added the spikes, because they thought, well, maybe that's what stars look like. But in fact, we know what a star looks like because we have the sun nearby. Stars aren't just points, and they're not even just like big giant circles of light. They're complicated objects. They have geometry. They're 3D. They're not uniform. They have bright spots and dark spots and little bubbles. So why can't we use a telescope to look at a star and see something like the sun, like that? That's because the size of something in the sky depends on how big it is and how far away it is. And this is something called the angular diameter. So there's a little bit of math, but it's not too complicated. So the idea is, you're looking at a star that's far away, and there's this angle in the sky that you're looking toward. And depending on how far away, big D it is, and how big it is, little d, you're going to get some sort of number. And there's this arc sign, there's this function for an angle, but this angle is very small because the object is so far away. So you can use this other equation where you have this constant in front to convert it to something called arc seconds, which if you hold your thumb out, that's a degree, and a degree has 60 seconds, and then there are 60 arc seconds, so there's 3,600 arc seconds in a degree. So if you divide your thumb into 3,600 pieces, you get an arc per second. So that's the idea, right? So that's this equation for angular size. And then the ability of a telescope to resolve something based on angular size depends on the size of the lens of the mirror you have and then the wavelength of the light. So how does this work? Here's a little demo. So say you have two stars far away. And if you have a big mirror, what you get outside of the other side of the lens are going to be these two spots. And this 1.22 comes from the location of these peaks. So these are the peaks of the light, and this is 1.22. So the point is, that's the limit at which you can separate the 2 points of light. If your lens is a little smaller, the points of light start to merge together. And then if the lens is quite small, you can no longer distinguish the two separate points. So the idea here then is bigger telescopes, bigger lenses are going to be able to have better resolution. So perhaps, if you think about the biggest star in the sky, Betelgeuse, sometimes called Betelgeuse, has an angular resolution of 40 milliarcseconds. So 40 of these, little tiny pieces of your thumb. So what size telescope would you need for that? So you can do the math. If you look at, say, the infrared, so 1.6 times 10 to the negative 6 meters, you find that you need a telescope that's 10 meters wide to resolve the star. So there is a telescope out there that's not big right now. It's in the Canary Islands. It's 10 meters. So one telescope on Earth could resolve Betelgeuse. What about the sun? So say we take the sun and we put it at the distance of the closest star, which is Proxima Centauri. Its angular diameter would be 7.2 milliarseconds, so much smaller. That would require a telescope 56 meters in diameter to resolve the sun at that distance. So the largest telescopes we're building in the next decade are up to 30 meters in diameter, and they cost billions and billions of dollars. Here's an example. This is a animation of what's called the European Extremely Large Telescope. So a bunch of the countries in Europe are building this giant telescope. It'll be the biggest telescope on Earth, done sometime probably in the next 10 years. And even that giant telescope couldn't resolve the sun if it was the distance of the closest star. And that closest star is actually much, much smaller than the sun, so we won't be able to resolve that star. So then how do we study stars? What can we do to study stars if they're so small and so far away? So there's a trick. There's another technique we can use called interferometry. So this uses, this actually, the bend here works really well. So this uses the fact that light is a wave. You heard that light is a wave, right? So light's a wave, and if you imagine that you have a wave here, and these are the white parts are the peaks, and the red parts are the dips in the light. It's coming in, and if you have two telescopes, you get this wave, and it comes at different times, and you put it in a lab, and when you combine waves together, they interfere, right? So you can use this interference in the study what you're looking at in the sky. Because they arrive at different points, you need something called delay, because you have to have the waves meet at exactly the same position for this interference to happen. But this interference from the combination of light gives us information about what the telescopes are looking at. You have something called the visibility amplitude. So that's just like the peak of the fringes from the interference of the light, and then you have the phase, which is where the peaks are. And they're both impacted a little bit by the wobbliness of the atmosphere, but the phase especially is. So keep that in the back of your minds. But an interferometer has a resolution as well. And the resolution, instead of being the size of the mirrors, is determined by the baseline. So the separation of these two telescopes is an also the wavelength. So you can imagine you can separate telescopes from really far away, and then it behaves like a giant telescope. The trick being, you just have to have a way to combine that light. So say you have a bunch of mirrors and some tubes, and you put it in a lab. So it's kind of abstract, right? But so these fringes then, how can we get any information about a star using that? So we take these fringes, and for instance, there's a measure of these tabs called the visibility, and it comes from the amplitude of these fringes, so the amplitude of the combined light. So if you take the normalized version of the stuff of like how much this variation is, and you plot it, you get a graph like this. And it turns out that there's this really handy mathematical relationship between how big a star is in the sky and what kind of pattern it makes. So we can work that math backwards, and we can determine, based on what those fringes that we observe look like, how big the star is. So a really small star in the sky is going to make this big, long function, whereas a bigger star is going to have a slightly smaller function. But we can plot that data out. We can collect that data, measure how bright the fringes are, and determine how big the star is. And so that's one way we can start to measure stars that are far away, just by combining the light. And that's what we do at CHARA. So CHARA is an array of telescopes that Georgia State operates outside of Los Angeles on a mountain called Mount Wilson. So it's really close to Los Angeles. You can, like, on the cliffs outside of the mountain, look down and see Pasadena. And you might think, okay, so why would you put a bunch of telescopes next to one of the biggest cities in the country? Isn't it going to be too bright? Well, there's a couple of things. One is that the weather in Los Angeles is such that often during the night, fog covers the city, so it actually gets quite dark up there. The other thing is, these telescopes here are all small. They're 1 meter telescopes, so we're not looking at really dim objects. We're looking at stuff that is relatively bright in the sky, and so the lights from Los Angeles matter a little bit less for what we're doing. But here's what happens. We have these 6 telescopes in different spots, and each telescope has the mirrors, and it extends the light from the mirrors down to a bunch of tubes. And these tubes all meet up in a lab. And in the lab, the lab is this really long building, and so all the light from these tubes gets combined here, then in the lab. And so what I have here is an example of the carts. So like I said, you need to have the delay to have everything match up. So the carts that do delay are on this really long hallway. And there are these little carts with mirrors, and they move like fractions of like millimeters precisely to line everything up perfectly. And when you do the observation, you're basically clicking these carts back and forth, tiny amounts to make everything line up. But that light gets then sent into various detectors, and you get the fringes. Okay, so CHARA is the separation of the biggest separation of the telescopes is 330 meters. So what kind of resolution can you get there? You get a resolution of half a milliarcsecond, which means if you're looking at like the visible, you can resolve the sun if it were 60 light years away. So now you're suddenly able to look at a whole bunch of stars in the sky and not just measure them, but get details in them. So this is weird, but okay. So I said the atmosphere messes up the phase, right? So what's happening here is these telescopes are looking at slightly different parts of the sky, and there's different, there's winds, the temperatures are a little different above the ground. There's all sorts of different things that influence what the light has to travel through, and that messes up the phase data. And you might think, why does it matter? I have permission to use my advisor's picture. Okay, so this is my advisor. This is advisor, this is chimp, right? PDF to be converted well. Okay, so phases are critical. So that's just their picture. If I swap their phase, the phase of the images, but keep just the amplitude part of the image, this is what happens. So this has my advisor's amplitude, but I switched it with the chimp's phase. And so you see the phase of the light contains most of the information about what something looks like. So you need the phase to see what a star looks like. So what do you do then if the atmosphere is messing it all up? You use this trick. If you have 3 or more telescopes, each baseline contains phase information from each of the different combinations. That's what's happening here. And if you add them all up, the atmospheric phase cancels out. So that's another thing that we collect. We collect the phase, the amplitude information, so how bright the fringes are, and then we collect this combination of the phases called closure phase. Those two things together give us everything we need to study what stars look like. And the more telescopes you have, the more information you get back. So CHARA, we have 6 telescopes, we get almost 70% of the information back. If you have 21 telescopes, which is what they want to build in the future, you get 90%. So more telescopes are good. So what has CHARA been able to do using these techniques? Here are some examples. One thing that CHARA was able to do early on was image the shapes of stars. And what they learned was there are a lot of stars that rotate so fast that they're not circular. They're broadened out. So these are actually some of these stars are quite bright. We've seen them before in the sky. And it turns out they're not just points of light, they're not just circles even, but they're broadened out. Another thing they were able to do was measure a supernova. So a supernova happens in the sky, and they said, let's see what happens to the supernova over time. And so they measured the size of the supernova over time and compared it to the theory, and we were able to test how supernova behave. The next 2 are movies. We're actually able to make movies of stars. So, see if it works. I hope it works. Is it just a picture? There it is. All right, so some stars orbit each other, and some stars orbit each other so close they interact. So here's an example of a movie CHARA made, imaging 2 stars that are close enough to interact. So you can see the light going to the one star being deformed by the presence of the other star as it orbits. This can only be done with CHARA. Here's the other one. You can see that. Another one is a giant star. They studied this giant star over the course of months, and they were able to make a movie of it rotating and following a spot. So just like the sun has magnetic spots, this star has magnetic spots, and you can see them moving, there it is again, on the star. That's pretty cool. I think it is. I'm not going to lie, I agree. So, okay, let's get this back to...
Even I think it's cool.
Was that Wade show? The movie? No, the movie, which one? This was a guy in Michigan. Rings out. And that's Rachel Rautenbacher from the University of Michigan. Those are two University of Michigan people, actually. This is almost all you. This is a GSU person. Gail, right? Gail, that's Gail. A lot of those other ones University of Michigan because they built the instrument that does a lot of the imaging. So they do the science first. Yeah. All right. So Betelgeuse. Oops, I said it 3 times. It's Halloween, right? Happy Halloween. Betelgeuse is a red supergiant star. I study red supergiants. Okay. I don't think you've seen that movie, but get the joke. Okay. Oh my God. I mean, it's coming from Mr. Movie book, right? Yeah. All right. Okay. So, all right. So Betelgeuse. It's a red supergiant star. Red supergiants are among the biggest stars in the universe in terms of their size. So you're familiar with what happens with like the sun and it becomes a giant, right? So something similar happens with massive stars. They are no longer diffused on the center of the core to make helium. So they start doing the reactions that make heavier elements using helium in the core. So the same thing happens, they expand, except this time they expand to be huge. So they end up being 100 to 1,500 times the size of the sun. They end up being up to 300,000 times as bright as the sun. They're a little cooler than the sun. But they come from stars that are about 9 to 25 times the mass of the sun. These stars eventually die as supernova and become black holes and neutron stars depending on the mass. And that's an important part of the question is how much mass do they have when they end? The thing is, these stars are so big that the gravity on them is really loose. So they cast out lots of material and they lose a lot of mass. And the question is, how much mass do they lose? How do they lose mass? We're not sure. One clue about the behavior of these stars is their photometry. So, red supergiants, they vary in their brightness. And they vary in their brightness in this really messy way. They're either slowly irregular or slowly semi-irregular. But in any case, there's not a lot of order to what sort of variations they are. But what we see is that they have variations of like a magnitude. And the variations can be hundreds of days to thousands of days. So some researchers back in the 70s went through the theory of how gas moves inside a star and compared it to the variations they see in red supergiants. And they noticed that if you come up with the theory of convection, so convection meaning hot stuff rises and then cools and then sinks, they found that, so in the sun, we see these little bubbles, that picture I showed. There's lots of tiny little convection cells. And as red supergiant, these convection cells would be 10, 25% the size of the star. They'd be huge, and they last hundreds of thousands of days. So the theory then is variations that we see in the light could be caused by the rise and fall in the convection cells, and this might contribute to mass loss. So that's what I'm interested in, is seeing whether we can see these convection cells. There's a movie of what modern theory shows. So when you make a movie of what a red supergiant might look like with convection, okay. Well, we'll forget about that.
Imagination time?
Imagination time. Imagine big, giant, bubbly, red, bubbles on a red star, and that's what you get.
Show us an interpretive dance.
I am not. Where'd I go?
Was Kramer on your committee?
No.
Full screen. Okay. Well, don't worry about that. Okay. So Hubble actually tried to image Betelgeuse, and they were able to do. Hubble's outside the Earth's atmosphere, so it has a little bit of advantage for resolving things. But the best they could do is that they noticed there's a hot spot on it. So there might be these large convection cells. Can we do better? So earlier interferometers tried to do something similar with red supergiants, and they too noticed single bright spots on the surface of these stars. But these are lower resolution interferometers. Is it possible that these stars actually have lots of spots like the sun does? That's where CHARA comes in. So CHARA is much more powerful than all the other interferometers. And if you look at a simulation of what CHARA could observe with a red supergiant so this is what a simulation of a red supergiant looks like. Using a simulation of a red supergiant, you notice that with the longer baseline, so this is like baseline essentially, the longer baseline that CHARA has, we can get more details of the surface of the star. So that's what I tried to do. Now, the problem is, if you think back to that picture of CHARA I had, there's 6 telescopes in different spots, right? A real telescope can be thought of as an interferometer with telescopes everywhere. So we only have little bits and pieces of that telescope that we're collecting data from. So there's a lot of holes in our data for making a complete picture. So that's the trick of what I study then, is how do you make an image from a little bit of data? And so what you do then is you ask yourself, I've got the data and the errors of the data. Then I know a little bit about what I'm looking at. I know I'm looking at a star. I know that the star has certain types of behavior. So I put in that information as well. And doing these two things together helps me figure out what the most probable image would be. That's the trick. So it's a combination of something called likelihood, which comes from the data, and regularization, which comes from my expectation of what the object should look like, and what sort of mathematical functions I can put in to help it put things together. This is not easy. So this is some of my real data. So if I tell my programs, here's my data, and I know that the image is going to be positive. There's like no such thing as like stars that are not like the opposite of bright, like negative brightness. And then normalize is just part of the behavior of an interferometer. I get this, which is clearly not what a star looks like. If I say, okay, I know the star is going to be somewhat circular, and I have to have these other qualities, I get something like that. And I still know that's not right. So then if I give it some function, I make it really, really strong, it looks a little better, but now it looks like I'm like pushing it too hard. So you have to find some sort of balance. You have to ask yourself, what's the best approach to solve this problem? So that's where my research comes in then, is figuring out how do I make an image of a red supergiant and then making it. So what I do is I take a simulation and I convolve it. So convolve means I make it look like an object going through a normal telescope. And then I use that as an input to a simulation. So I take the data, my real data, and copy the quality of the real data. That's what's going on. That's just a sort of a cartoon of what that would look like. And then I go through my method and I try to make a picture. And what I do then is I compare the result from there, that second one. Okay, anyway. I compare the result to the original input and determine what method works the best. How do I get closest to what I think it should look like with what I have out? So that's the first step for coming up with how you reconstruct the picture of a star. Then you have to ask yourself, when I have these spots in an image like that, are they real or are they just kind of like the result of me telling it what to do, or maybe there's more data in that part of the image than there is in others? So then you can do a test. You can say, do the same experiment, except this time you just give it like a circle with a boundary. Make a big observation of it, and then go through the same sort of reconstruction process again, and see what you get. And so there, it should ideally look like this. It's not going to look like this because this isn't completely filled in. But what I have instead then is something that looks a lot different than this. So that's encouraging, right? So that's sort of an area where this is an example of the noise in my data. That the image on the right shows the noisier parts of the data. But there's still more that I need to do to verify what I'm looking at. That's determining the error from my process of reconstruction, my process of piecing together the data to make an image. So what I can do today is I can reconstruct using slightly different starting locations, slightly different starting spots in the image process, and have these different results, and average them all together, and then I can get a standard deviation and a mean. And then this is my final output image. This is the thing that I can track the most. So when I do that, then I know if I get images. And so what I've done is I've looked at a star, a bunch of stars, and one star in particular for like 6 years now, actually. Called Lazy Fig. It's just a star in Cygnus. It's 4 million arc seconds, which is much, much smaller than they don't use, but it's a good size for what I'm trying to do. And what I've been doing is looking at it to see how the spots change. So each image is from a different year, and what you see then is the star is changing, the spots are changing size. This all makes more sense if you saw the movie of the simulation. The spots are changing size, location. So it seems like the theory of how these stars behave is sort of close. My next thing to do is fill in the gaps. So I'm looking at the same star for 6 months in a row to see how these stars change from month to month, because it's possible that 1 year apart is a lot of time. Maybe the spots are actually changing from month to month, which would be an interesting discovery. And also I want to measure how big the spots are relative to the size of the star, how that fits with what theory predicts, how long they last, and this will all tell us what's going on inside the star, and also help us understand how much mass is getting lost, which helps with the predictions of supernovas. But for me, part of it is just like making really detailed images of stars or spots. It's kind of cool. So that's everything. Do you have any questions about interferometry? Let's give them a hand. Okay.
Two questions that are kind of related to each other.
Yeah.
Does the height of the telescopes relative to each other have any effect on your data? And if you did the 21 scope setup, would it be the same trigonal layout, or would it be?
Those are both really interesting questions. So the first one, yeah, it does a little, so that impacts the delay. So, because they're going to have, I think they try to keep the height somewhat similar because the tubes get kind of weird in terms of design if they're not. But yeah, so that all gets corrected in the lab.
Gotcha.
But yeah, that's part of the delay. And then the layout for the 21 telescope is actually an open design question right now. The Y pattern is popular for a variety of reasons, but it's not the only way of doing things. And in fact, the 21 telescopes, there might be something better.
Okay, the carts, you can control those from downtown, right? That's what you're actually
You can
controlling?
control anything. Yeah,
That's what I thought.
yeah, that's all. I mean,
So it's all automated too. You can run everything from downtown Atlanta on Mount Wilson with minor help from, some people who live on the mountain to go out and when things get stuck, have them stuck then.
Right. In fact, it's almost like a video game. So especially with what I do, I control 6 telescopes at once. I'm controlling lots of different card combinations, and it's you push left, push right, and then you're looking at whether or not you get a fringe, because you have a video like whether or not you get fringes. Well, there it is. Stop. It's very busy. You have to keep watching.
But it's still amazing to know you can control the world's largest optical interferometer from 2,000 miles away.
It is incredible.
Real time.
It's amazing for a company like the computers, and also amazing from like internet. It's much more reliable than it was, even like 10 years ago.
I'm sure.
Any other questions?
Most of the time, I'm sorry, this is a regular star.
These are old.
These are really old. These are massive old stars, red supergiants. They're old for their lifetime, but young compared to the sun because they don't last very long. But they're big. They're huge stars, so they behave differently than the sun because they're so big.
So besides the fact that you wanted to be positive and probably a disk, was there any other regularizer that really helped you out?
Yeah, so what I found useful are a couple functions. So there's something called a Laplacian. So Laplacian is basically asking about the difference of the difference between pixels. So you first look at the difference between 2 pixels, and you look at how that difference is different from another difference next to it. So the idea then is these stars have bright spots and dark spots, so that means that there's changes between the different pixels. So asking functions that ask about how the pixels vary between themselves has been really useful for me. Looking for ones that that smooth out major differences, but allow differences within neighboring regions has been really useful as well, because that's sort of what these stars look like. In fact, when I've gone through, though, I come up with new functions. One thing that's been useful, believe it or not, is looking at MRI of the brain papers that do the same thing but imaging the brain. Because the brain has they got lines and bright spots and dark spots. Brains and stars from a really superficial imaging standpoint look kind of similar. So that was sort of helpful, because I am not good enough at the math to come up with my own function, but I'm good enough to figure out how to apply other functions that people have used. Anything else?
I know you said no questions, but don't judge.
No judging.
So I was confused. It sounds like you were saying you can't just keep a picture of
Okay, so yeah, I might have been, that's my fault if that's what you heard. So the sun is close enough we can do that, right? The sun is close, but that's the only area you can do that for. The other ones are just too far away, so you have to use interferometry because we can't build a telescope big enough.
Could be that she misunderstood. We said take the sun and put it where the nearest star would be, and you can't see it.
Yeah.
Put it one parsec away. Yeah. And you need a 56-meter telescope to see it.
Right.
Or to make out the tips.
Yeah.
That video from the folks at University of Michigan of the two stars,
Yeah.
how long time-wise?
That's several days. So those stars rotate very
Okay.
yeah.
Wow.
Still really cool.
Yeah.
It depends on, there's some stars that orbit in like, what, hours?
Hours, yeah.
Yeah, especially when you get those like close contact on it.
Right. I think that one is days. That's a couple of days. So you do that is observed. So I think each for start of the night into the night, start of the night into the night, kind of thing.
So why don't we give a round of applause for all of our speakers? Thank you guys so much for coming down. I really appreciate it. I hope they appreciate some of it.
All that extra credit.
All that extra credit. Well, some of it was credit, like they had to do it for lab. That was why there was a bit of an exit.